So hello, welcome to a video explaining how ocean waves act as a fractal. So if you look at ocean waves in nature, they kind of look like this, where they start at a base point and then they keep an angle of rotation until a top part where they'll collapse due to gravity. So if we look at the base point here, it stays about the same, and they keep the same angle of rotation with a medium-sized radius, then it collapses. So I created 3 simulations explaining the different factors on waves, on ocean waves. So if you look at the script here, it's just a normal JavaScript script in the P5 library. And all the link to all these scripts can be found in the description of this video on the GitHub page and on our article that'll be linking as well. So yeah, it's just a basic HTML linking to the JavaScript script. So if you look at the first script, I just created a basic wave with a slider. So if we move the slider, we can see that it's just a wave that you would see normally. So if we look at the base part here, we can see that it kind of gets shorter after every iteration. Well, definitely the width of this wave gets shorter. But it keeps the same base point, which is what these ocean waves do. They keep the same base point and just collapse onto one thing. But if we look at the top of this wave, we can see that the angle of rotation here I set at 30 degrees. It keeps the same angle of rotation and the same size, just like a fractal, and then it just collapses at one point. So that's the representation, but what if we include different factors that impact waves in nature, such as the wind? So let's say we increase the degrees of rotation due to the wind. So let's say the wind pushes on a wave, so like in wind waves. This is a wind wave, where we see that the base stays around the same here, and then it rotates at a very high angle and would just collapse. So the radius of this wave isn't big, just a small circle, but the angle of rotation here is quite big. So if I take another normal tide wave at around 60 degrees, so this is the same size tide sorry, as this one, but the angle of rotation is twice the size of the other one. So if we just do the simulation, you can see that it already just completely changes angle, and then it'll just collapse. So the radius is a lot smaller than the radius we have here. Now, what about other factors such as tides? So if we look at a tsunami, you can see that it's very, very, very high tides with like a low angle of rotation. It doesn't really rotate over here. It just kind of goes high, high, high because of the high tides, and it'll crash in. So with the simulation, I took it about the angle of 22.5 degrees, which is just a bit less than the general wave over here, and the high tide of about 200 pixels compared to the 150 pixels the other ones. So if we start off the simulation, you can see that it goes very, very high, and over here would about crash. All of the tides here would just crash down here. So if you look at a tsunami wave, it's pretty representative of what it does. Look at the pictures here. You can see that it gets very, very high, not a very big angle of rotation, and then just crashes down. So yeah, so these simulations represent how they kind of act in nature. So it's kind of an accurate representation. So we can see that they actually use some sorts of fractals. So they keep the same angle of rotation, and then due to gravity, they would obviously crash. Now, for the wind waves, we can see that this representation isn't totally accurate. Like that doesn't necessarily determine the power of the waves if we increase the angle. So obviously this doesn't look like it's a big wave, but the speed of the wave is definitely higher due to the wind pushing on it. So let's not forget that the speed of the wave would definitely hit at a higher impact than a general wave, but it would have not as big of an angle of rotation, so it wouldn't be as big. So yeah, that's pretty much it. Thank you.